Okay, so the next equation, or the next topic we're going to talk about, is the Henderson Hasselbalch equation. So this is an equation that you probably learned and then probably forgot in general chemistry, but we need to revisit it because it's going to be a very useful equation both in the lab and in lecture and in problem solving. So this is an equation, for me at least, it's very difficult to remember if I haven't thought about it for a couple of days or a week or even a month. So I'm going to revisit the equation, write it down, and then hopefully give you a very easy way of always remembering the form of the Henderson-Hasselbalch equation. So the general form of the Henderson-Hasselbalch is pH equals pKa plus the log of the conjugate base over the acid. So it's the log of the concentration of the conjugate base over the concentration of the acid. I've got a very easy mnemonic to help you try to remember this if it's been a while. So it's going to be these three parts that are included in the mnemonic. And the mnemonic is hippie kids always drop the acid. So hippie kids always drop the acid, always is positive. So hippie kids always drop the acid. So you might see the Henderson-Hasselbalch like this, or you might be able to see the Henderson-Hasselbalch in this equation, and it would still be correct. So I'm going to go ahead and rewrite it. And so again, the way to remember this is going to be with the H, the K, the negative sign, and then this part right here, the base. Okay, so it actually goes along quite well with this mnemonic up above, and if you can, you might see this coming, but if not, the mnemonic is hippie kids, if positive is always, negative is never, hippie kids never drop the base. So if you think about dubstep and something like that, you can't really expect or envision the hippie kid to be listening to dubstep. So this is one way to think about the Henderson-Hasselbalch. And again, both ways are totally valid. So what is the Henderson-Hasselbalch actually even useful for? This is another part that actually kind of gets lost in trying to talk about the intricacies of the Henderson-Hasselbalch. So one thing to remember is that pH is really just the negative log of the concentration of the H plus molecules. So when you see pH, you're really trying to express the concentration of H plus in solution. Okay, so what we're really doing with the Henderson-Hasselbalch is we're relating the concentration of the H plus ions in solution to the equilibrium constant of a certain acid. And so, again, the equilibrium constant is a relationship between A minus and HA. So we can talk about the concentration of H plus ions in solution if we have information regarding the pKa of a molecule and the concentrations of that molecule. So what we can also do, and what we normally try to use this for in organic chemistry, is determining the protonation or deprotonation state of an acid. Okay, so what we're going to try to do is use this equation to figure out when a molecule is protonated and when a molecule is deprotonated. And we're going to try to go through this exercise by thinking about three separate scenarios. So we can think about three scenarios for how a molecule can be in a protonated or deprotonated state. Okay, so let's just make this a ratio of the acid to the conjugate base. So let's just say maybe we have a 50-50 mix of the acid and the base. So this 50-50 is, pretty easy to really think about numerically, but just to make it a little bit more explicit, let's try to talk about this in terms of pictorial forms. Okay, so now what we're really saying is that we have a 50-50 mix of the acid and base. So for our case, let's just make our acid blue, and let's make our conjugate base red. So we want to know under what conditions, under what pH conditions, will we actually have this 50-50 mix. So let's go ahead and copy and paste the Henderson-Hasselbalch and try to figure this out. So in this case, we've already said that HA and A minus is going to be a 50-50 mix. So what we can do is say pH is going to be equal to pKa minus log of 50-50. And 50-50 reduces to 1, and it turns out that the natural log of 1 is going to be 0. So this whole term ends up going to 0. And so it turns out we can say that now if the pH of the solution is equal to the pKa of any particular acid, then we're going to have a 50-50 mix of that acid being protonated and that acid being deprotonated. Okay, so pH equals pKa. So if you, let's say, had a molecule who had a pKa close to 10, if the pH was 10, then you'd have to 50-50 mix of the molecule being protonated and deprotonated. Okay, so now let's talk about another scenario where maybe we'll have a mix of something being in an acid to conjugate base form of maybe we'll have one acid for every 100 conjugate bases. So that would be this kind of scenario right here, where we have, one HA for maybe 100 A minuses. So let's go ahead and take this guy and move it up. So this is the pictorial form of what you would get if you had an HA to A ratio of maybe 1 to 100. So now what we're going to do is see what the Henderson Hasselbalch tells us about what kind of pH we need to have the molecule be completely deprotonated. And we're going to have 100 on the bottom. This reduces down to -2. So in this case, what Henderson Hasselbalch will be telling us is that if we want to have this situation where we want our acid to be completely deprotonated by 100 times, we are going to have a situation where we have a pH value that's equal to pKa plus 2. So let's say the pKa of our molecule would be 10. We would need a pH of 12 to completely deprotonate it. Okay, so that makes sense because the pH is more basic than the pKa. So we have, for every one deprotonated form, we have 100 protonated forms. So if we were to plug it back into the Henderson Hasselbalch, what we'd find is that in this case, we have 100 more protonated molecules than deprotonated molecules. And so what we find is that this guy reduces to 2 as well, or 2 instead of -2. So what we'll find then is if we plug it back in, we're going to find that in order to have this situation where 100 of our molecules will be protonated and one will be deprotonated, we're going to have a pH that's related to the pKa by having the pKa -2. So the pH is going to have to be 2 units below, or 2 units more acidic than the pKa in order to protonate everything. So again, if we had a molecule with a pKa of 10, we'd have to have a pH of 8 to ensure that everything is protonated.